Hello and thank you for watching. In this video we're going to introduce the notion of sequences. So to start off, a sequence is just a function from the natural numbers to the real numbers, a real sequence. And this assigns every natural number n a real value xn. So for example, say we have xn equal to 2n minus 1, for example, and we want to see which numbers it goes to. So we have that x1 is equal to 1, x2 is equal to 3, x3 is equal to 5, and so on. We may also define sequences recursively, so we may say xn is equal to n xn minus 1. Okay, so in this case, let's have the initial condition that x1 is equal to 1. So x1 is equal to 1, x2 is equal to 2 times 1 equals what? Equals 2. x3 is equal to 3 times 2, which is equal to 6, and so on. In this particular case, we can say that xn is equal to n factorial, which is fairly obvious, but in general, we may not always be able to find some closed form or explicit way to write out the sequence. So sometimes we write it out recursively and just leave it recursively. Or sometimes there might not even be a closed form. So for example, if we have something like xn equals square root of xn minus 1 plus xn minus 2 floor of this minus xn minus 3n over e to the n, and this is also to the n. Well, this might not have a closed form, this might have a closed form, I'm not sure. But in any case, it's really hard to find, and we may want to leave it in terms of this with whatever initial conditions. So now I'm going to introduce limits to infinity in terms of sequences. So we've looked at regular limits before, and we had that, say we have x minus some c being less than delta implies that fx minus L is less than some epsilon. We had this before. Now, limits to infinity are very similar in the sense that if, say, xn converges to x, we write that for every epsilon greater than 0, there exists an n in the naturals such that xn minus x is less than epsilon for all n greater than this big N. Okay. You can already see the similarities. And as explained previously, we want to say, okay, if you give me some epsilon, if you tell me how close you want to be to this limit, then I'll give you some, before it was delta, now I'll give you some n, some term in a sequence such that for every term after that, it's going to be this distance away or closer. So to give an example, let's say we have xn equal to 1 over n. 1 over n. Let's look at the first few terms. This gives like 1 over 1, 1 over 2, 1 over 3, so on. Eventually we'll give like 1 over 101. In any case, it gets smaller and smaller, so we have reasons to believe that it may converge to 0. So I'm going to claim x in this case is 0. And we want to show this, so we'll say that, okay, let's claim that for any epsilon greater than 0, there exists some n greater than n, such that this is true. There exists some natural n for which such that when we take any term that's after that, it will also be less than epsilon. So, okay, we can rewrite this. We know that xn is 1 over n, so we have 1 over n is less than epsilon, but this is positive for natural numbers, so we have that 1 over n is less than epsilon, which then implies that since both are positive, we have n is greater than 1 over epsilon. Hang on, we want to find some big N for which this is true, so why don't we set our n equal to 1 over epsilon, and now working backwards, we can just reverse all the steps, and we'll get that, okay, 1 over n is less than epsilon, which means that 1 over n minus 0, and since both this is positive and also epsilon is positive, we can just take the modulus, and this will be true. So now I'm basically saying, okay, give me an epsilon, so say epsilon's like 0.001, for example, and I'll say, okay, if we take the 1 over epsilon, if we take the 1 over epsilon term, then every term after that will be this distance away from 0. So if we take epsilon to be this, then we'll take n equal to be 1 over epsilon, which is equal to 1000. So I'm saying, okay, even though the terms before that may or may not go to get closer than this epsilon, we can guarantee that every term after the 1000th term. So we have that x 1001, x 1002, and so on. These are all going to be less than 0.001, because we're basically saying that this is the distance away from 0, and this is how close we want to be. So we showed that for 1 over epsilon, so 1 over this distance, every term after that is going to be this close to it. Okay. Now, to leave the viewer with some exercises, I want to say exercises. Firstly, I want to say prove the limit laws for sequences. That is, if we have, for example, one limit law is that if we have, for example, limit as n goes to infinity, so this is what we've been formalizing this whole time, of some an plus bn, this is equal to the limit of an plus the limit of bn. Now, if you're struggling with this, then you should refer back to a video where I covered this for different limits for non-sequences. Okay. Secondly, prove that 1 over n squared also converges to 0. Lastly, prove that minus 1 to the n does not converge. That is, it diverges, and therefore we cannot find some natural number n such that every distance is going to be less than epsilon. Yep. Okay, that's all. Thank you for watching. Bye bye.